So, if you're standing on a site right now, staring at a reverse osmosis skid, and you've ever wondered why your permeate TDS, your total dissolved solids, starts mysteriously drifting upward the second the summer heat hits.
Right.
Or, I mean, why a recycled O-ring that saved you like 50 Rand just cost you a massive multi-thousand Rand call-out fee. You are definitely going to want to hear this deep dive.
Oh, absolutely.
Because our mission today is to just completely cut through the marketing brochures, the ones that promise plug-and-play water treatment. We're getting down to the actual physics and the hard metric numbers that really dictate whether a plant survives or fails.
Yeah, because the water flowing through those pipes, it doesn't read the marketing brochures. It just doesn't.
Exactly.
It only obeys pressure and chemistry. And, working with engineers and technicians on the ground across South Africa, the most common failures we see, well, they happen when a system is operated based on assumptions instead of the physical realities of the hardware.
Yeah, and we're pulling our data today directly from the technical engineering articles sitting right now in the knowledge base on the DWT website. So no fluff, just the mechanical realities.
Right, the hard facts.
So I guess before we even look at the high pressure pumps or the physical membranes, we have to talk about what we're actually fighting against. Because water fundamentally wants to do the exact opposite of what an RO plant forces it to do. Right?
It really does. I mean, it basically comes down to osmosis.
Right.
If you take a tank and put fresh water on one side of a semi-permeable membrane and salty water on the other side, nature just demands equilibrium.
Wants to balance it out.
Exactly. The fresh water will naturally push through that barrier to dilute the salt side. And the strength of that natural pull, well, that's what we call osmotic pressure, and we can actually quantify it.
Okay, so what's the number?
It's a physical force of roughly 0.7 bar for every 1,000 milligrams per liter of dissolved salts.
Okay, so to put that in perspective, if I'm pulling from, let's say, a standard brackish borehole with maybe 2,000 milligrams per liter of TDS, I'm basically fighting an invisible wall of about 1.4 bar before my plant has even produced a single drop of clean water.
Yeah, exactly. And honestly, that's just a mild borehole.
Right.
If you're dealing with coastal seawater, which is roughly 35,000 milligrams per liter, that invisible wall is around 25 bar.
Wow. 25 bar just to break even.
Just to stand still.
Right.
So to achieve reverse osmosis, your high pressure pump has to completely overpower that natural osmotic pull and then apply enough excess pressure on top of that to actually force the water backward through the membrane, leaving all the dissolved ions behind.
I used to picture an RO membrane as just a really, really microscopic sieve, like a high-tech coffee filter, I guess, where you just smash water into a dead end until the clean stuff comes out the bottom and the dirt gets stuck on top.
A lot of people think that.
But mechanically, that would clog in, 5 minutes?
Oh, less than that. Yeah, it's actually a cross-flow system. The cross-flow mechanism is really the only reason industrial reverse osmosis is even possible.
Okay, so how does that work in the tube?
So you have one stream going in under high pressure, but two streams coming out. The feed water flows horizontally across the surface of the membrane.
Not directly into it?
Right, across it. A percentage of that water is forced through the microscopic pores to become your clean permeated. But the remainder of that water stays on the feed side. It essentially acts as a high-speed river that sweeps up all the rejected salts and suspended solids and just carries them out the back end as the concentrate stream.
Okay, so that concentrate stream, what some people incorrectly call the waste stream, is actually a crucial housekeeping service.
Yes, exactly.
Which means if an operator looks at a plant and thinks, I'm going to throttle the concentrate valve shut just a little bit more to squeeze some extra clean water out, they aren't optimizing the plant at all. They're essentially firing the cleaning staff.
That's a great way to put it. They're completely blinding the membrane. When you starve that crossflow, the dirt and salts just drop out of suspension and coat the membrane surface. Which really brings us to the 3 operational numbers you absolutely have to balance.
Right. Rejection, recovery, and flux.
Exactly.
So let's unpack those. Starting with rejection, I mean, modern brackish elements hold back over 99% of salts under standard test conditions, right?
Under test conditions, yes. But out in the field, you're measuring the system's overall rejection. And that constantly drifts depending on the age of the elements, your operating pressure, and, well, the temperature.
Okay, and then you have recovery. This is the percentage of your raw feed water that you actually convert into clean permeate.
Right. And this is a strict design choice. It's not something you just tweak on a whim because you feel like it.
Like tweaking the valve.
Exactly. A small, simple skid might run at maybe 30 to 50% recovery. But a large industrial train with extensive pretreatment, that can push 70 to 80%.
Wait, okay, hold on. If I'm running a plant at 75% recovery, that means 3/4 of the water is being stripped away as clean permeatus.
Correct.
Doesn't that mean the concentrate stream leaving the tail end of the system is intensely concentrated? I mean, it must be 4 times as salty as the feed water. Why doesn't that just immediately cement the back-end pipework solid with scale?
Oh, it absolutely wants to. That is the exact reason we rely on advanced pretreatment, which we'll definitely get into shortly, because you are essentially building a scaling machine at the back end of the plant.
Wow. Okay, and the final number driving that machine is flux.
Right. Flux is the rate at which permeate passes through a specific area of membrane. It's measured in LMH liters per square meter per hour. On a clean, brackish feed, you usually design for a flux of 20 to 30 LMH.
And if you push that flux too high by ramping up the pump, you're just dragging dirt onto the membrane surface far faster than your cross-flow housekeeping service can actually sweep it away.
Exactly. And this is where operators get so confused on site. People look at the pressure gauge and treat it like a setting on a dial.
Like volume on a radio.
Right. But pressure is a consequence, it's not a setting. The pump simply provides whatever physical force the system demands to achieve your targeted flux and recovery while fighting against the feed's osmotic pressure.
So if your required pressure is steadily rising over a month just to keep your permeate flow stable, the pump isn't broken. It's just working harder to push water through an accumulating layer of dirt.
Precisely.
Okay, so that explains the mechanical pressure. But what about the temperature drift? I mentioned in the intro the permeates TDS changes in the summer. Why does the actual chemical quality of the water change just because the ambient temperature went up?
Well, it's pure physics. The polymer matrix of the membrane, it physically expands and becomes more flexible as it warms up.
Oh, like any plastic.
Exactly. The rule of thumb is that water permeates about 3% faster for every degree Celsius you go up. But because that matrix is slightly more open, salt passes through faster too. So in the summer heat, your plant actually makes more water at a lower pressure, but that water is slightly saltier. It's a physical reality of the material. It's not a fault in the system.
Okay, so if temperature can physically swell the membrane and change the output like that, the actual manufacturing chemistry of these membranes must be incredibly specific.
Oh, it's highly engineered.
Which means we can't just treat all reverse osmosis elements as identical tubes. You have to match the specific membrane chemistry to the TDS of your water.
So let's look at the DuPont FilmTec families as our baseline.
Sure, so every DuPont element balances a core chemical trade-off during manufacturing. They manipulate the thickness and the cross-linking of the polyamide layer.
Meaning what, exactly?
Well, tighter, denser membranes reject almost all the salt, but they require massive pressure to force water through, whereas looser polymer structures let water flow easily to save on energy, but they sacrifice a tiny bit of salt rejection.
Okay, let's start with the brackish workhorses then. If you have a feed up to about 8,000 milligrams per liter, the industry standard reference is the BW30, right? Yeah, the BW30. It gives you a highly reliable 99.5% rejection. If your permeate quality is the absolute most important factor, that is your default.
But let's say your feed TDS is a bit lower, maybe only 1,500 milligrams per liter, or maybe your client is just heavily focused on the plant's long-term electricity bill.
Right, energy costs are a big deal.
Definitely. So that is where you look at the LE and XLE families, right?
Yes.
Low energy and extra low energy.
Yes, exactly. Because DuPont engineered the polymer matrix to be slightly looser there, they only reject around 99.0 to 99.3% of salts. But the operational advantage is just huge.
Because of the pressure drop.
Right. An XLE element will produce the exact same amount of water as a BW30, but at less than half the feed pressure.
Wow. Which cuts the size of the high-pressure pump you need and slashes the electrical draw for the next 5 years.
Huge savings. And if a site demands both high rejection and low energy, they step up to the ECO family. That uses more advanced chemistry to optimize both sides of that equation.
And then, on the extreme end, you have the SW30 seawater heavyweights. I mean, these are built to handle feeds of 32,000 milligrams per liter and operate at crushing pressures between 55 and 83 bar.
Yep. And we also have specialty elements like the Fortilife range. Those are designed for high-fouling wastewater reuse, where the membrane surface is basically modified to resist organics sticking to it.
Right.
Or NF nanofiltration, which isn't strictly RO. It's a deliberately loose membrane that rejects large molecules like hardness and organics, but lets monovalent salts like sodium chloride pass right through.
Okay, I have to ask about the over-engineering trap.
Yeah.
Because I know technicians who think, I got a standard brackish borehole, But I want this plant to be absolutely bulletproof. So I'm going to buy the SW30 seawater membrane because it's built to handle 83 bar. My borehole only needs 15 bar. This thing will outlive me. Why is that a terrible idea?
I hear that all the time. It sounds logical, but mechanically it is a massive mistake.
Why?
If you put a heavy-duty seawater membrane onto a low-pressure brackish feed, you are operating entirely outside of the element's design envelope. At those low pressures, the water won't distribute evenly across that extremely tight seawater membrane surface.
Just sort of channels.
Exactly. You get localized dead zones, severe flux imbalances, and really rapid scaling. The element will just underperform and foul prematurely.
So you really have to match the physical tool to the specific osmotic job.
Always. Which leads directly to the golden rule of membrane loading. You can never, ever mix different element types in a single pressure vessel.
Not even to experiment.
Never. If you put an XLE low-energy element in the same tube as a tight BW30, the water is just going to take the path of least resistance. It will flood through the XLE, totally exceeding its maximum flux limit, and foul it instantly, while the BW30 just starves. You ruin the whole array and never hit the numbers on either datasheet.
Okay, so let's say you've done all the math. You've sized everything perfectly, picked the exact right FilmTec membrane for your specific water chemistry, and loaded the vessels correctly. If I take raw municipal or borehole water and pump it straight into those highly engineered elements, what actually happens inside that tube?
You are handing the plant a death sentence. Literally.
Just immediately.
Immediately. People forget that a spiral wound RO element is essentially a meter of tightly rolled plastic with feed channels that are roughly 0.5 millimeter wide.
0.5 millimeter.
Yes. So every single grain of sand, every microbe, and every chemical oxidant in your raw water is being violently forced into that 0.5 millimeter gap. Pretreatment is not an accessory. It is the armor your membrane absolutely relies on to survive.
Okay, let's break down the 3 specific killers that pretreatment has to eliminate. First up, chlorine. I've actually heard operators say that leaving a tiny bit of chlorine in the feed water is a good thing because it prevents bacterial biofouling on the membrane.
Oh man, that is catastrophic advice.
Oh.
Polyamide membranes have effectively zero tolerance for chlorine. The technical specification demands free chlorine be below 0.1 milligrams per liter. But practically, on site, you treat it as absolute zero.
What does it actually do to the membrane?
Chlorine doesn't just block the membrane, it actively attacks the nitrogen-hydrogen bonds within the polyamide layer. It chemically unzips the molecular structure of the plastic, so it turns a microscopic filtration net into an open, gaping hole. And that damage is cumulative and completely irreversible.
Wow. Which means you absolutely must have activated carbon filtration or sodium metaphospholite dosing upstream.
Yes.
And you can't just install it and forget it, right? Because a spent carbon bed doesn't trigger an alarm. It just quietly lets the chlorine pass through and the RO membrane gets eaten alive.
Eaten alive, exactly.
Yeah. Okay, so the second killer is particles and colloids. And we aren't just talking about cloudy water here. We are talking about the SDI, the silt density index.
Right, the SDI is critical. It's not a simple turbidity measurement. You're not just looking at how clear the water is.
Okay.
The SDI is a physical test where you measure how quickly the raw water blocks a standardized 0.45 micron filter pad over 15 minutes. It basically tells you how sticky and microscopic the particulate matter is.
Okay, and what's the target there?
The absolute ceiling for RO is an SDI of 5. But for a stable plant, you really must design your upstream media or ultrafiltration to deliver an SDI below 3. If you achieve that, your membrane cleaning intervals can stretch from weeks into literally years.
Right after those media filters, just before the high-pressure pump, sits the 5-micron cartridge filter. Now, I see people treat that 5-micron cartridge like a kidney, thinking it's there to actively purify the water. But it's not a kidney, it's a goalie.
The goalie, I like that.
Yeah. By the time water hits that cartridge, it should already be perfectly clean. That filter is really just the final insurance policy to catch, a stray piece of PVC shaving from a pipe repair. Or sand blow by if a media valve fails, before it absolutely shreds that multi-million rand high-pressure pump.
Exactly right. When you look at the completely useless, you don't care about the feed water. You have to calculate the LSI of the concentrate stream because that is where the concentration factor peaks and the scaling risk actually lives.
Okay, so how do you manage it?
You manage it by either physically removing the hardness with the softener up front or by dosing an anti-scalant chemical that temporarily holds those salts in solution just long enough for them to exit the vessel.
But even with the best goalie, occasionally a ball gets through. Pretreatment slips up and the plant gets sick. I've noticed guys on site tend to use the terms fouling and scaling interchangeably, but mechanically, they are entirely different diseases,
Yeah.
and they strike in two completely different geographic locations on the skid.
Yes, and this is diagnostic gold for any technician. Let's look at the physical geography of the plant. Fouling is the buildup of suspended dirt, organics, and biological slime. Now, where does that raw dirt hit first?
The front.
Exactly. It hits the very front of the plant. The lead elements of the first stage end up acting as very expensive depth filters for whatever your pretreatment let through.
Right. While scaling, which is those dissolved salts crystallizing into rock that doesn't happen at the front, it hits the tail elements at the very back of the final stage, because that is where the water has been concentrated to its absolute maximum.
Precisely. So you don't even need to open the pressure vessels to know what's wrong. You just need your weekly logs of normalized flow, pressure, and salt passage. If your differential pressure, your delta P, is rising rapidly in stage 1, but your permeate quality is mostly fine, you have a physical fouling problem at the front.
But if you see a distinct rise in salt passage, meaning your permeate water is suddenly getting saltier and the differential pressure is creeping up in the back end of the plant, that is scaling. The hard scale crystals are literally physically forcing their way into the polyamide layer, disrupting the membrane's ability to reject salt.
Exactly. And when you identify either of those signatures, you clean immediately. The rule is to clean at a 10 to 15% loss of normalized flow. If you wait for a 30% loss, the dirt or scale has become so heavily compacted that the cleaning chemicals physically cannot penetrate the flow channels.
And the order of those cleaning chemicals is a matter of life and death for the membrane.
It really is.
Because alkaline, high pH cleaners dissolve organics and biofouling. Acid, low pH cleaners dissolve mineral scale. But if a plant is suffering from both, does it actually matter which chemical you circulate first?
It matters immensely. You must always circulate the alkaline cleaner first.
Always.
Always. If you push a low pH acid into a membrane that is coated in a layer of organic biofouling, the acid will instantly coagulate the proteins in that slime. It will chemically set that organic layer, literally baking it into the polyamide, much like frying an egg in a hot pan.
Oh, wow.
Yeah, and once you fry that organic layer onto the membrane, no chemical on Earth will get it off. Always alkaline first to strip the organics, then acid to dissolve the scale beneath it.
I love that visual. Do not fry the egg on your RO membrane.
Check.
Now, we've talked extensively about the delicate chemistry, the microscopic polymers, and the water itself. But let's look at the heavy physical hardware holding all of this chaos together. We're pushing corrosive, high-pressure water through these systems. How do the tubes holding the membranes not just burst?
Well, they're housed in filament-wound FRP fiber-reinforced polymer pressure vessels. And the first major design choice is in-port versus side-port configurations. In-port vessels take the feed water directly in through the end cap closures. They're cheaper and great for a simple single-vessel skid.
But the absolute headache comes when it's time to actually service them. Because to pull an element out of an end-port vessel, you have to physically unbolt and break apart all your heavy, high-pressure pipework manifolds.
Yeah, it's a nightmare.
Which is why side-port vessels are the absolute standard for any multi-vessel industrial skid. The water enters through ports on the side of the shell, meaning you can pop the end caps off and push the membranes out without ever touching the plumbing. It just saves hours of wrench time.
Definitely. You also have to rate those FRP vessels correctly. You might buy a 21 bar or 31 bar vessel for brackish water, or maybe a 69 bar vessel for seawater. But the critical safety detail is that the vessel must be rated for the maximum pressure the pump can physically produce during a deadhead situation, not just your daily operating pressure.
Right, because if a motorized valve slams shut unexpectedly, a positive displacement pump will find that pressure ceiling instantly. And you do not want the vessel to be the weakest link.
Nobody wants that.
And when things go wrong mechanically inside those vessels, it drives operators crazy. You get a sudden spike in your permeate TDS. The site manager panics, assumes the membranes have totally failed, and is ready to drop tens of thousands of rand on replacement elements. But the actual salty permeate mechanic is often infuriatingly simple, isn't it?
It almost always is. If you see a sudden shear step change in your permeate conductivity, it is a mechanical bypass.
Okay, and what's the leading cause?
Reuse closure seals. A technician decides to use a worn O-ring just one more time to save a few rands. Or they install a brine seal backwards. That allows the raw, high-pressure feed water to completely bypass the membrane and shoot straight down the gap between the element and the vessel wall, mixing directly into the clean permeate.
It is maddening to think about.
Yeah.
A rubber seal worth a fraction of the cal-out fee, causing a massive site panic. The lesson is simple. Replace the O-rings every single time you open a vessel.
Yes, it perfectly ties our diagnostic signatures together, too. Let's recap them. A sudden, sharp step change in TDS, that's mechanical. Check your O-rings and seals.
Right.
A slow, steady climb in TDS with a rising differential pressure at the back of the plant. That's scaling. But what if your salt rejection drops plant-wide and your permeate flow actually increases?
That's the chlorine damage we talked about.
Yeah.
The polymer bonds have been eaten alive, and the membrane has essentially become a very expensive empty pipe.
Correct. And finally, before that water leaves the skid, we need to set expectations for the permeate itself, because even a perfectly healthy RO plant does not produce chemically pure H2O.
Right. Because of the rejection physics, you should expect your permeate TDS to be roughly 1 to 4% of your feed TDS. So if your borehole is 1,000 milligrams per liter, you're getting maybe 10 to 40 milligrams per liter out, which is brilliant, high-quality drinking water, but it's
Yeah.
not absolute zero.
No, it's not. And critically, it is slightly acidic. Because our membranes only reject dissolved ions, gas is passed right through. So any dissolved CO2 in the feed water sails straight through the membrane, dropping the permeate pH to anywhere between 5 and 6.5.
Wow.
Yeah, this makes the final product what we call hungry water. It is entirely unbuffered.
So what happens if you send that water straight into distribution?
It will aggressively pull minerals from cementitious storage tanks or corrode copper pipework. You almost always have to run it through a limestone remineralization bed or dose caustic to correct the pH before it leaves the plant.
Okay, so let's bring all this together. Running a reverse osmosis plant successfully, right here in South Africa, isn't about buying a magic box and hoping for the best. It comes down to respecting the fundamental physics of crossflow. It means matching your specific DuPont FilmTec membrane chemistry precisely to your feed TDS and your energy budget.
Absolutely. It means ruthlessly defending your pretreatment parameters, guaranteeing zero chlorine, maintaining an SDI below 3, and constantly monitoring the LSI of your concentrate stream.
And most importantly, keeping that weekly log of normalized flow, salt passage, and stage-by-stage differential pressure. Because long-term trends diagnose problems, while daily snapshots just leave you guessing. And remember, all of the exact metric numbers, the sizing guidelines, and the chemical mechanics we unpack today, they are living right now in the knowledge base on the DWT website. Go pull those articles up and read them before your next site visit.
It really is the absolute best way to bridge the gap between theoretical engineering and actual plant survival in the field.
We're going to leave you with one final thought to ponder as you head back out to the plant today. We started this deep dive talking about cal-out fees and the industry obsession with the RO membranes themselves. But if a reverse osmosis system is essentially just an incredibly sensitive, highly expensive instrument for testing exactly how good your upstream pretreatment is, are we spending all our daily maintenance time looking at the wrong end of the plant? Think about those 5-micron filters. Until next time.